Hello and welcome to AICE Chemistry Lecture Series. In this video, we're going to start Chapter 8, which is going to focus on equilibria. This is a really long chapter compared to some of the last ones we've been looking at. And this chapter is fairly important to understand because it's going to connect to a lot of the other sections on other chapters that we see in physical chemistry. So let's get started by looking at the sections. There's going to be 7 sections in this chapter, with the one practical being another titration. This particular titration is an acid-base titration. So the idea of that is going to be the same as what we saw before, just with an acid-base reaction, which we'll touch upon later in the chapter. But chapter 8 is going to have 7 theory sections. Section 1 is on just what is a reversible reaction and equilibrium. Section 2 will start talking about how equilibrium changes depending on the different things that we can control. In section 3, we'll start talking about the mathematics that go along with equilibrium, looking at things like the equilibrium constant and the equilibrium expression. In section 4, we'll talk about the exact same topic of equilibrium constant and expression, but particularly with gas reactions using pressure. In 5, we'll talk about how equilibrium is used in the chemical industry, so we're going to look at very specific reactions. Then in section 6, we'll start talking about acid-base reactions, and particularly acid-base equilibrium. And finally, we'll end the discussion with indicators and acid-base titrations and how those specifics tie into that acid-base reactions that we talked about earlier. But for now, let's jump into section 1. Section 1, let's talk about the basics, right? What is equilibrium and what is a reversible reaction? Because we cannot talk about equilibrium without first talking about how certain reactions are going to be reversible. So that's what 8.1 is going to be about. So reversible reactions. Some reactions can actually be reversed. We think of reactions as going in one direction. For example, the dehydration of hydrated copper sulfate into anhydrous copper sulfate and water separately. However, certain reactions like this one are reversible reactions. And all that means is that it's a reaction in which products can be changed back to the reactants by reversing the conditions that caused them. For example, if we have hydrated copper sulfate and we heat it, it turns into the anhydrous copper sulfate and water separately. Well, if we simply just combine the copper sulfate with the water again, that reaction can be reversed in the opposite direction, meaning the products become the reactants now and create again the hydrated copper sulfate. This is a very crude and basic reaction that does this, but a lot of different chemical reactions are reversible. Most chemical reactions that require heat, for example, or that require cooling, can be reversed by just simply reversing the temperature change. Now, some reversible reactions, though, never completely go in one direction. The reactants never completely turn to the products. That's what we know as an equilibrium reaction. Equilibrium reactions are reactions that do not go to completion. They do not turn every single reactant into a product. So the reactant and the products are present in fixed concentrations and ratios during the reaction. So for example, when we react hydrogen gas with iodine gas, it produces hydrogen iodide gas. However, in reality, this reaction, which is reversible, meaning hydrogen iodide gas can be turned to iodine and H2, never goes to completion. Essentially, what happens is that some of the hydrogen and iodine molecules are going to start reacting, creating the HI, the hydrogen iodide. But as more and more of the hydrogen iodide is created, it starts to decompose back into hydrogen and iodine separately. That back and forth keeps happening essentially forever. That's what an equilibrium reaction is. As the reactants become the products, as the forward reaction, what we call it, as the forward reaction happens, so thus, eventually, as we get more and more of that product, the reverse reaction happens. So as hydrogen and iodine become HI, HI starts to break down and become H2 and I2. So it's this kind of loop of a reaction. Because a reaction is reversible, it undergoes what we call equilibrium. The forward reaction happens, and then as it creates more and more product, the reverse reaction happens at the same time. So whenever we have a container of H2 and I2, we're never going to have that container completely turn into a container of HI. It's going to keep going back and forth and back and forth. Meaning that if we do have a container of these compounds, or of HI and I2, so if we have a container, and we'll put hydrogen as pink, so pink is going to be H2, and then blue is going to be I2, as the hydrogen and the iodine react with each other, they're going to create HI, which we'll put here in green. Well, the HI also breaks apart and turns into H2 and I2, back and forth, back and forth. So at any one time, this container has all three of our chemicals. It has H2, I2, which are reacting together to become HI, and it has HI, which is decomposing into H2 and I2. So because it's back and forth, back and forth, back and forth all the time in this reaction, that container is never going to have just H2 and I2. It's never going to have just HI. It's always going to have a mixture of all of them. That's what we call an equilibrium reaction. It's an equilibrium because the forward and reverse reactions are happening constantly all the time in both directions. And so we're never going to have one or the other reactants or products. We're going to have a mixture of both. So let's keep looking at this. So there are four different characteristics of equilibrium. Any reaction that is in equilibrium state, and we call this a state because equilibrium reactions eventually reach an equilibrium state, has four features. So equilibrium reactions like the one we just discussed, the reaction of H2 and I2 to create HI, are going to be denoted by this double arrow. And that double arrow is essentially showing that it's going in both directions. That is what denotes an equilibrium reaction. Equilibrium reactions, once we let hydrogen and iodine react, that reaction will start making HI. Eventually, it will reach what we call the equilibrium state. So even though they have the same name, they're two slightly separate things. The equilibrium reaction is a reaction which can go in both directions, and it's a reaction which will eventually reach the equilibrium state. Now, what is the equilibrium state? The equilibrium state has four different characteristics. So reaction reaches the equilibrium state when it's dynamic, and we're going to look at each one of these individually in its own slide. So equilibrium state is dynamic. The forward and the reverse reactions that we just talked about are occurring not just at the same time, but at the same rate, meaning the rate of the reaction is equal. They're going just as quickly as each other. The concentration of the reactants and the products remain constant, meaning that even though the reactants are becoming the products and the products are becoming the reactants, their concentrations do not change. As one reactant gets created, one reactant gets used up to create a product. So they have the concentrations of the reactants and the products are constant. And then finally, it requires a closed system. So it's in a closed system. So let's talk about each of these four characteristics of equilibrium state in their own individual slides. So let's talk about dynamic equilibrium first. And this is the one that gets most people. It's not necessarily the most important one because you will maybe be asked a question of what does it mean by the term dynamic? What do you understand by the term dynamic? But it is not something where we have a skill, right? There's no math associated with it or anything like that. But dynamic equilibrium. Usually we visualize chemical reactions as the reactants becoming the products and all at once, and that's it. So normally, anytime we talked about H2 becoming reacting with I2 to become HI, what we envision is that the hydrogen and the iodine react. Every single molecule reacts, and they all become HI. So we go from maybe having, let's say, 10 particles of this and 10 particles of this to having and 0 of this, to then once the reaction happens, 0 hydrogen, 0 iodine, and 10 HIs, right? Well, 20 HIs. That's not necessarily the case, though. The reactions don't just happen. They don't all become the reactant and the products all at once. And especially in equilibrium reactions, this does not just happen in one direction. In those equilibrium reactions, this is going to happen in both directions, meaning that the reactants are not just becoming the products are becoming the reactant as well. This doesn't, so whenever we visualize a chemical reaction as just happening, it doesn't work for equilibrium. Because equilibrium is said to be dynamic. So we have dynamic equilibriums. It means that the reactants are being converted to the products at the same rate as the products are being converted to the reactants. So at the same rate at the same time. Meaning that if we have one hydrogen and one iodine becoming 2HI, at the exact same time we have 2 HIs becoming a hydrogen and iodine. The forward and the reverse reactions are never going to stop, even if we have a specific amount of each reactant and chemical and product. So even if we have, let's say, 5 molecules of this, 5 molecules of this, and 10 of this, as one of these and one of these are becoming 2 of these, 2 of these are reacting to become 1 of each of these. So it's constantly going in both directions. Even though there's no visible change, there's no change in concentration, there's no visible change in the reaction, nothing seems to happen. Because the equilibrium is dynamic, it's constantly happening in both directions. So that's what a dynamic equilibrium means. It just means that as the reaction progresses, both the forward and reverse reaction are happening at the same time. So it's always something happening. Even though it might not seem like it's happening, there's always the forward and reverse reaction happening. They're just happening as quickly as each other. So let's look at our next point. The next characteristic of equilibrium, which the equilibrium state, which kind of goes along with that, is that there's an equal forward and reverse rate of reaction. We will discuss rates in more detail in chapter 9, but rates are essentially how quickly the reaction is going, the speed of the reaction. At equilibrium, the forward and reverse reaction are happening at the same time, but also at the same rate. And that's kind of plays into the whole dynamic equilibrium bit. It's that when equilibrium state is reached, once an equation or a reaction has said to be reached equilibrium, the reverse and forward reactions are going to happen at the same time and at the same rate, at the same speed. The reactants are being converted to the products just as quickly at the same speed as the products are being converted into the reactants. We do not automatically start this way though. So for example, if we look at this chart that we have here, you'll notice this is a chart of the rate of the reaction versus time. You'll notice that here, so let's just say for the sake of having something to look at, we have the reactants and we have an equilibrium reaction where reactants become the products. Just because, and I'm actually going to put this in 2 different colors here. So we have the forward reaction, which is when the reactants become the products, and we have the reverse reaction, which is when the products become the reactants. If we look at this graph right here, we can actually start the reaction from either direction. We can start the reaction with a lot of reactants, let's say 100% of the chemicals are reactants, and 0% are the products. So the forward reaction happens first. Or we can start a reaction where we start with nothing but the products. So we have 100% of all the chemicals are present are products, and 0% are reactants, meaning the reverse reaction is going to happen. Because remember, since this is reversible, this can go in either direction. Or we could even have a reaction where we have 50-50. 50% of the chemicals are products, 50% of the chemicals are reactants, and both the reverse and forward reaction are happening at the same time. So if we start a reaction with only reactants, we get the forward reaction. If we started with only products, we get the reverse reaction. This is a case of the latter, a case where we start with 100% products. So the reverse reaction happens. Notice how we start with the reverse reaction rate being really high up and the forward reaction rate being really low, meaning that we're starting with more products and reactants. But what happens? As the reaction proceeds, as products become reactants, the amount of products is going to decrease. So the rate of the reaction, how quickly the reaction happens, is going to depend on how much of that product we have. As the reverse reaction happens more and more and we lose products, that rate decreases, and we can see that because this goes down, but eventually it plateaus. On the other hand, as we convert more and more of these products into the reactants, the rate of the forward reaction, the blue one, is going to start to increase. As we have more and more of those reactants for the forward reaction, that reaction happens more and more quickly. Eventually, we reach equilibrium when both the rate of the reverse and forward reactions even out and become the same. As the reactants get transformed into the products, or vice versa, the rate of the forward and reverse reactions slowly start to trend towards each other. Whatever we start with more of, if it's the products, then the reverse reaction starts to slow down as we use them up. Or if it's the reactants, then the forward reaction starts to slow down as we use them up. But it's just going to depend, right? It's going to depend on what we call this. If we were to do the opposite, start with 100%. Let me raise this. If we were to start with 100% reactants and 0% products, all the difference that this will make is that instead of calling this the reverse reaction, we'll call this the forward reaction. Because the forward reaction will start happening really quickly and then slowing down. And then instead of this being the forward reaction, this will be the reverse reaction. When we have a lot of the reactant for something, that reaction is going to happen very quickly. Whereas when we have very little of it, it's going to happen very slowly. And so, depending on what we start with the most, we are going to have either a forward reaction that happens really quickly, or a reverse reaction that happens really quickly. But whatever starts really quick is going to slow down over time. Whatever starts very slow is going to speed up over time. Eventually, once they both reach the exact same speed, that's what we call the equilibrium state. And that's why we say that both the reverse and forward reaction have the same rate at equilibrium, because they're happening just as quickly as each other. That's why it's a dynamic equilibrium. That's why nothing seems to change. Because as we're converting, let's say, 10 molecules of reactants into 10 molecules of products, 10 molecules of products are also being converted to 10 molecules of the reactants by the reverse reaction just as quickly. And so once the rates of the forward and reverse reaction are the same, we say we have achieved the equilibrium state for this equilibrium reaction. So that's the second characteristic. Let's look at the third. The third characteristic is similar, but you have to be very careful with how you word this. The concentrations of the reactants and the products at equilibrium are constant. At the equilibrium state, the concentration of the reactants and the products are constant. Not the same, that's the rates, they're constant. There is a difference, and this is something where you need to be very, very careful with your wording when you're answering these Cambridge style questions. Something being constant and something being the same are not the same thing. When we say two things are the same, we mean that they have the same identical number. Whereas when we say they're constant, that means they stop changing. Now, they could be constant and the same, but they could also be constant and different. The concentration of the reactants and the products at equilibrium do not change. They may not be the same, but they are going to be constant because they do not change. And that's because the rates of the forward and reverse reactions are equal. are the same. So because of characteristic 2, characteristic 3 happens. We do not automatically start with constant concentrations. For example, let's look at the equation that we were talking about earlier. Hydrogen and iodine creating HI. Well, since this is an equilibrium reaction, if we start with all hydrogen and iodine, so we start with, again, going back to the 100%. So if we start with nothing but hydrogen and iodine, which is what this is showing, and 0 HI, what's going to happen is that as the forward reaction happens, as hydrogen and iodine become HI, the concentration, which is on the y-axis, of hydrogen and iodine are going to start to drop. And the concentration of the HI, which was 0 initially, is going to start to go up. But as more and more of this HI is being created, the reverse reaction starts to happen as well, where HI is turned into H2 and I2. So as the reaction happens, as this reaction occurs, the reverse reaction starts to occur as more and more of that product builds up. That's why this H2 and I2 concentration don't just keep dropping to 0. That would happen if the reaction was not an equilibrium reaction. But because as we create HI, it slowly starts going back and turning to H2 and I2, that backwards reaction starts creating H2 and I2, meaning that that concentration of those chemicals are not going to just go to 0. They're going to start to slowly equalize. They're going to start to slowly become constant, not the same, constant. As the HI is being created, again, because the reverse reaction starts to happen, it starts using up that HI. And so we see this increase in HI slow down and eventually again become constant. Why? Eventually, the rates of the forward and reverse reaction become equal to each other. If 20 molecules of H2 and I2 are becoming 40 molecules of HI per second, then 20 molecules or 40 molecules of HI are becoming 20 molecules of H2 and I2 per second as well. When the rates are constant, when the same number of molecules are being used up as are being created, nothing seems to happen. The concentrations don't change, but it is dynamic because it is happening. The rates are the same, the rates are equal, but the concentrations at equilibrium become constant. They don't change. They become the same concentration for the reactants all the time and for the products all the time, but not necessarily the same as each other. This equilibrium can be achieved from either direction. This down here is the opposite situation. Imagine if we instead started with 100% HI and 0 of H2 and I2. Well, the opposite will happen. We'll start with really high HI concentrations and 0 H2 and I2. As we start to use up that HI, the concentration of HI drops, but it eventually stabilizes. As the H2 and I2 get created, the reverse reaction starts to happen where H2 and I2 start becoming HI. So we start going in both directions. As the H2 and I2 are being created, their concentration goes up, but eventually stabilizes once the rates of the forward and reverse reaction, let's say 20, become the same. As we create 20 H2s, we use up 20 H2s. As we create 20 I2s, we use up 20 I2s. So eventually those concentrations are going to stabilize, become constant, and again, be careful with your wording, not the same, constant. And so eventually we reach that equilibrium, and so equilibrium has been achieved. So at equilibrium, the concentrations of the reactants of the products are constant, not the same, constant. Now, one other thing that I should mention is by how much they change. So if we look at, we're just going to use the bottom one because it's easier to look at, but this is true of both of these. If we look at the changes in hydrogen, iodide, HI, from here to here, if we call this X, and then we look at the changes in concentration for the H2 and I2 individually, notice how this, which is 1, 2, 3, 4, and this one's 1, 2, 3, 4, 5, 6, 7, and there should be an eighth one that actually starts a little higher, so we'll call this 8. So you'll notice how this change, it will be better set to be 2x, and this change is x. So the HI concentration changes by twice as much as the X concentration, or the H2 and I2 concentration. Why is that? Well, that's because of the coefficients. If we look at the coefficients, we have a 2 in front of the HI, a 1 in front of the H2, and a 1 in front of the I2. Meaning that we are going to use up HI twice as fast as we are going to create H2, or vice versa. That's why the concentration changes are twice as much for HI than they are for H2 or I2 individually. You gotta keep that in mind because ratios are often part of these questions. Realize that the stoichiometric, even though this is an equilibrium reaction and eventually we're gonna reach equilibrium and the concentrations are gonna be constant, the ratios that the coefficients give us are still valid. And so if we make, or if we use up from the initial, which is what is up here, this is the initial concentration of HI. So we can call this, so we can call this concentration of HI initially. That is going to change by twice as much once we reach the concentration of HI at equilibrium than the concentration of, let's say, and this is going to be the same for H2 and I2 because they're equivalent to each other, but let's say H2. The initial concentration of H2 to the equilibrium concentration of H2 is going to be a different change, right? Because since this is a 2-to-1 ratio, the concentration of H2 changes by X, in this case 4 ticks, whereas the one for HI is going to change by twice that number because of that 2-to-1 ratio. So in this case, 8 ticks. So do keep that in mind when it comes to the ratios of the coefficients in an equilibrium reaction. Those are still applicable and they're going to come into play with our math later on. But yeah, that is the third characteristic of an equilibrium, is that the concentrations of the reactants and the products will be constant at equilibrium once we reach equilibrium state. And finally, the fourth and last one, which is not really so much a characteristic but a necessity. Equilibrium requires what we call a closed system. And we talked about this with thermodynamics, but a closed system is essentially a system where neither reactants nor products, or any kind of matter, can escape the reaction mixture. It is necessary for equilibrium to be reached because in order for the reactants to react with each other and become the products, and vice versa, we need to keep those chemicals in the same place so they can actually react and interact with each other. So, for example, if we had something like calcium carbonate, which when it is heated up becomes calcium oxide and carbon dioxide. So calcium carbonate, which is in red, when heated up, it's a solid. It becomes calcium oxide in green, which is also solid, but it also becomes carbon dioxide, which is in white here. If we have a closed system, that carbon dioxide molecules are able to just bounce around the container and eventually meet up with a calcium oxide again to become calcium carbonate. So this reaction is reversible only because the carbon dioxide is allowed to be in contact with a calcium oxide that is created, and therefore that allows them to actually interact and do the backwards reaction. If we had an open system, on the other hand, once calcium carbonate reacted with calcium, or was heated up and became calcium oxide, the carbon dioxide would escape the system. It will never have a chance to react with the calcium oxide again for the reverse reaction to happen. Because of this, equilibrium reactions require a closed system so that the products of the forward reaction can actually be kept in constant touch with each other so they can actually undergo the reverse reaction. Because if one of those products is allowed to escape, then the reverse reaction cannot happen. So that's why an equilibrium reaction, to reach equilibrium state, needs a closed system. One where neither the reactants nor the products can escape and everything is constantly in touch with the other. So those are the four, going back to the equilibrium, those are the four things that are required for equilibrium state to be reached. We need to know that it's a dynamic equilibrium where the forward and reverse reactions are happening at the same time. We need to have both the reverse and forward reactions occur at the same rate, at the same speed, which will lead to the concentrations of the reactants and products remaining constant, not changing because the reverse and forward reaction are happening, again, at the same speed. And finally, we are required to have a closed system for these reactions so that the reactants and the products are in constant interaction with each other and both the reverse and forward reaction can occur. That's it for section 1. That's the basics of equilibrium and equilibrium states. I'll see you all in the next video.